So question 1, leading coefficient test. The purpose of leading coefficient test is to determine the end behavior of a polynomial function. So it tells us what's happening to far left and far right of the graph. So as x goes to negative infinity, this would be like the left side of the graph, and as x goes to positive infinity, this would be like the right side of the graph. Okay, it's called leading coefficient test because you need to be looking at the leading coefficient, and you care whether it is positive or negative. And you need to look at the degree, and you care if it is an even number degree or an odd number degree. Not that it's an even function or an odd function. I know that sounds very similar, but whether the degree is an even number or an odd number. And then there's really only 4 possibilities, so I'll just go ahead and say what those are. Either a positive leading coefficient and an even degree, like positive x squared. It could be a negative leading coefficient and an even degree, like negative x squared. It could be a positive leading coefficient and an odd number degree, like positive x cubed. Or a negative leading coefficient with an odd number degree, like negative x cubed. These are the only 4 possibilities. Now, these graphs are way more complex. If all we care about is the end behavior, then that's all we have to compare it to. So, number 1a has a negative leading coefficient. I don't care that it's negative 2, I don't care that it's negative. And an odd number degree. So it's going to have the same end behavior as this other one that has a negative leading coefficient and an odd degree. It will be going up to the left, down to the right. B has a positive leading coefficient and an even degree. So it would have the same end behavior as positive x squared, because it also has a positive leading coefficient and an even degree. So both up. C, positive leading coefficient odd degree, just like positive leading coefficient odd degree, goes down to the left, up to the right. And negative leading coefficient even degree, just like negative x squared, goes down to the left and down to the right. So in the back of my mind, I always use these 4 just kind of as a template. In fact, it's really only kind of like 2. You think about the end behavior of x squared and x cubed, negative x squared is just flipped over the x-axis, and negative x cubed is just flipped over the x-axis. Okay, so that's a good approach to that. All right, last class we talked about the divisions, long division and synthetic division. So long division has this as a setup. Synthetic division that as a setup. If this stuff is not in standard position, you're welcome to rearrange it so that it is. That's always a good idea. Synthetic division, if there's something missing, like if there's no x squared, you have to put a 0 there. You have to have those placeholders. But then both of these are algorithms, so there's a few steps to them, and we just repeat those steps as often as we can. So the long division algorithm says the first part of your quotient is the thing times 2x that gives you 4x cubed. So it would be 2x squared. This times this, it goes here. But it actually goes to all of this. It's being distributed, so it's also a minus 6x squared. And if you take my advice, since you're really subtracting all of this, instead change the signs in half. So those are the long division steps. I just need to repeat it again, and looks like even maybe one more time after that. So our next piece would be 4x, because 4x times 2x is 8x squared. And also 4x times negative 3 is negative 12x. Change the signs and add to ensure that you're actually subtracting that stuff. And a lot of times you only have to do the sub steps twice, but it looks like we can go a third time here. Because 3 times 2x is 6x. You change the signs. I almost didn't do that myself. And it looks like the remainder is 6. So, quotient plus remainder over divisor. Now, for that particular one, you need to also understand that long division is necessary. You cannot use synthetic division there based on what you're divided by. And technically, that's not exactly true. You can actually use synthetic division because it's linear, but there's one extra step, and it still doesn't work all the time. So, in general, if it's not just x plus a number, x minus a number, just use long division. So for synthetic division, the algorithm's a little bit easier, and this is why people seem to prefer. We add it down, so 2 plus nothing, put that there. We multiply that by what was in the top left, and put it here. And then those are the only 2 steps. So repeat them, add down, multiply, and put it here. Add down, multiply, and put it here. Add down. And finally, you need to interpret those numbers. The last number should always be your remainder. The number before that should be your constant. The number before that should be your number of x's. The number before that should be your x squared. All of those are only going to be in the right place, though, if you're sure that you don't have any placeholders. This one didn't have any placeholders. Remainder still needs to be put over divisor. Same purpose. Approach. Now, just because I'm recommending you not to use synthetic division on number 2, on your test, I guess you can still go back and do the long division to make sure that you have the same answer. You had time to do a good way to check this. Alright, on to question 4, Descartes' rule of signs. And this is probably the one that's going to vary whether you saw this or not last year. It's not a hard topic, but it also is not all that useful. It does give us some new information. It's just that we don't need it very often. Okay, so Descartes' rule of signs tells us how many possible real zero or positive real zeros we have and negative real zeros we have. So if we try to find the zeros of this function, some of them would be positive, some of them would be negative. Descartes' rule of signs gives us an idea of how many of each of them would be. How many of them are positive, how many are negative. Okay, so what you have to do to find the number positive, I like this one in red and do the word red, and I'll do the other one in a different color. You want to count up the number of sign changes. So like this is positive, and then the next thing is negative. The next thing is positive, the next thing is positive, the next thing is negative. So from one to the next, here's one sign change. Here's a second sign change. That's not a sign change, but that's a sign change. There's 3 sign changes. That means that the zeros of this function, there's either 3 of those, or subtract 2 from that, 1. And you just keep subtracting 2 until it doesn't make sense. So I don't need to subtract 2 again because you're not being negative 1. So 3 sign changes, and there could be 3 positive real zeros, or 2 less than that, or 2 less than that, or 2 less than that. So software makes sense. So I don't know if 3 of them are real zeros, or positive real zeros, or 1 of them is positive real zero. But I know there's not 2, I know there's not 4, I know there's not 5. Still more information than we had before. For negative, real zeros, you also count up the sign changes, but you have to count up the sign changes of f of negative x. So you have to think about everywhere there's an x in this function, we're actually plugging in a negative x. And some of the signs will change and some of them will not change. If I plug it in here, negative x times negative x times negative x times negative x times negative x to the fifth would be negative x to the fifth, basically because that's an odd number. Minus 2x to the fourth, but negative x times negative x times negative x times negative x would be positive, because 4 is even. You multiply an even thing, or a negative thing by itself an even number of times, so it'll stay positive. So what about this? If I replace this with negative x, what is this going to go to? And then this one would be, what was that thing? Okay, so you have to do that. And then you count the sign changes. Again, negative to negative is not a sign change. Negative to negative is not a sign change. Negative to positive is a sign change. Positive to negative is a sign change. 2 sign changes. Which means of the real zeros, 2 of them will be negative, or 2 less than that, or 2 less than that, or 2 less than that. Let's stop there. It doesn't make sense anymore. You can have negative zeros. Negative zeros. You can have negative and not have a zero. Alright, on to question 5, rational zero test. Okay, so rational zero test, one of the easiest things you do in all of Algebra 2, but also you don't usually just kind of get it pretty quickly, and then you don't worry about it, and so then you often forget it. But rational zero test is also kind of referred to as the P over Q list. Sometimes people remember that, where P is the constant, and Q is the leading coefficient. And the rational zero test says take plus or minus all of the factors of Q, so plus Q is 9. So factors are everything that go into it evenly, 1, 3, and 9. But we need plus or minus each one of those. Plus or minus 1, plus or minus 3, plus or minus 9. You have to put the plus or minus. If you're being lazy and you only put the plus or minus on the 1, it's not right. All of this plus or minus. Over plus or minus all the factors of P. So plus or minus all the factors of the leading coefficient. The leading coefficient here is 2. The factors of 2 are 1 and 2. So plus or minus 1, plus or minus 2. That's the answer. As in the text, it says don't actually find the zeros. This test is good to find the possible rational zeros. Yes. I put these backwards right here. Thank you. Go back to 6. Same thing, easy mistake for you to make as well if you figure out which ones to be able to. I kind of remember it as like out of the alphabetical order. Constants usually at the end, but you put P first, and leading coefficients usually at the beginning. Okay, so what this tells us is the possible rational zeros. It doesn't mean that all of these are rational zeros. And you don't have to expand this list out on a normal basis, but go ahead and do it for me here for one time so that you can see what this is. Basically, any of these 6 over any of these 4 are likely to be zeros of this function. So like 1 over 1, or negative 1 over 1, or 1 over 2, or negative 1 over 2, or 3 over 1, or negative 3 over 1, 3 over 2, or negative 3 over 2, it could be 9 over 2, or it could be 9 over 1, or negative 9 over 1, or it could be 9 over 2, or negative 9 over 2. So these two are saying the same things. We just don't like to expand it out like this. This is a nice condensed way to say the same thing. You won't ever have to expand that through the multiple choice questions would likely do that, so you need to know this. So how this is supposed to be helpful to you is like 4 is a rational number, but 4 is not in this list. So I have no idea what this graph looks like without thinking some effort behind it. I know that there's no chance that 4 is a 0 to this function because it's not in this list. I see 5 is not in this list. There's no way this touches the x-axis at 5, or 6, or 7. But maybe 9 halves. 9 halves is likely, but it's not guaranteed. It's just that it's a possible 0. This is a very easy list to make, and it gives us things that are likely to happen. We still like to do this. Okay, on to question 6. So this is a nice way, well, I said Precal science may be the only thing that came out from last year. You may not have seen upper and lower bounds, but it's not too difficult. Okay, so you can use synthetic division to test for an upper lower bound. What that means is you're going to divide this out. Your work is going to be synthetic division. Add and multiply, add and multiply, add and multiply. And there's something about that synthetic division that I see, looking at these values, that tells me that's upper bound. But first, what would it mean if I had a remainder of 0? Okay, so that would mean like 3 is a 0, right? If it divides into evenly. You remember that? Okay. If all of these are positive down here, that means 3 is an upper bound. What it means to be an upper bound is that there guarantees that there's no x value bigger than that are zeros. So the fact that 3 is an upper bound tells me that 4, 5, 6, 7, anything bigger will not be a 0 in this function. It will not cross the x-axis at 4, 5, 6, 7, 8, anything bigger. So you may want to add that in here. No zeros. So it's really, the work is really synthetic division, but you're just recognizing that all of these terms on the bottom are positive. Alright, you should also add the number 0 then counts as a positive or a negative, however you want it to be. So if this was actually positive 2, 0, 7, it would still be an upper bound, because 0 can be treated as a positive or negative. Okay. Alright, so lower bounds, we're going to do basically the same thing, so we're going to make a different observation. So we're going to do synthetic division. And if something is in lower bound, these values down here at the bottom will alternate between positive and negative. So that means x equals -1 is a lower bound for this equation. Positive, negative, positive, negative. Now, same thing, 0 can count as a positive or a negative. So if this was positive, 0, positive, negative, this would still be a lower bound. So you can work either direction. So what it means to be a lower bound, you should probably be able to guess now since I told you what outer bound is. Because this is a lower bound, there will be no zeros unless this if it's a lower bound. So if I'm trying to understand this function, if I'm trying to figure out what this graph looks like, recognizing that -1 is a lower bound tells me there's no chance anything smaller than that will be a 0. There's no chance there would be any x-intercepts to the left of that. So that's pretty helpful if you're trying to figure out what the graph looks like without it. On to number 7, the topic. Find the limiting factors of this, given that this is one of the factors. So, the second question we could do is we could either give you a calculator and you could graph it and you can see that it has a 0 of 3, which means it has a factor of x minus 3, or we could just take it for you in the direction type of work. But if this is a 0, you should be able to divide this out evenly. So if you want to do long division, you can, but based on how it's set up, I guess most of us would prefer to do synthetic division. And before I even do the synthetic division, what do I know is going to happen in this? The remainder better come out to 0. That's what it means for it to be a factor. So add down, multiply, add down, multiply, add down, multiply, the remainder 0. Now if we interpret what this means, this is how many x squareds, x's, and a constant. And here we don't need to say plus the remainder over the divisor because the remainder is 0. 0 divided by anything is 0. So we don't have to keep up with the remainder. So I want to get the remaining factors out of this. Well, the nice thing about this is it's quadratic. So worst case scenario is I use quadratic formula. Best case scenario is I figure out how it factors. Plus 2 and minus 5. You guys see that that's okay? Boys, this would be 3x squared. These would be minus 10. The outer part of FOIL would be 6x, and the inner part of FOIL would be minus 5x. That would be minus 5x. So here are our 2 other factors. So using a little bit of information to compress your polynomial down to a quadratic, from quadratic we have a small tools. Quadratic formula or factoring usually is at least one formula. That's another use of why we like to be able to divide. Again, I did synthetic division there, but if you really wanted to do long division, you could do simple. Okay. On to the last 3 questions are about rational functions. And specifically graphing rational functions. Not adding, subtracting, multiplying, and dividing, but what are the graphs look like? So part of a rational function you want to look at like this. Part of the time you want to look at factor. So the numerator doesn't factor, but the denominator factors like this. And dealing with rational functions is actually not too difficult, but there is a good handful of rules that if you don't know the rule to find a hole, then there's not much you can do to get it. If you don't know the rule to find vertical asymptotes, there's not much else you can do to get it. So holes occur, and I'm going to kind of pause between each of these to give you a chance to maybe write a few words to give yourself notes. But a hole occurs if there's a value that makes the numerator and the denominator 0 at the same time. The numerator equals 0 at -1, and the denominator equals 0 at 4 and -1. So because -1 makes the numerator and denominator 0, that's going to be the x value of the whole. To find the y value of the whole, you have to divide out those common factors, plug this in, and you get 1 over -5, so -1/5. Divide these out, plug in the x value into what's left. So the numerator doesn't just go away, that's a 1. 1 over -1 minus 4 would be -5. So 1 over -5 is -1. So try to summarize that in a few words to yourself. Even if you end up practicing it in the next few days, it's still a good idea to give yourself some notes. Okay. And then include it down here in the graph as an open circle. A hole doesn't actually fit your graph, so the only way for us to show that is with the open circle. So that's usually one of the harder things for people to get. Okay, vertical asymptotes were numbers that made only the denominator 0. So not -1, -1's already a whole. But +4 makes just the denominator 0. And asymptotes get graphed as dash lines. X equals 4, and this number that makes just the denominator 0. Okay, horizontal asymptote. You have to compare the degree of the numerator to the degree of the denominator, and there's 3 different things that can happen. The degree of the numerator can be bigger, and that's when you have a horizontal asymptote. The degrees can be equal, and that's when you put leading coefficient over leading coefficient for your horizontal asymptote. Or your degree of your denominator can be bigger, and that's when you get a horizontal asymptote of y to 0. To me, this question, and this question are all basically suggesting you do the same thing. They're suggesting, why don't you plug in some points into a table? Well, y-intercept is when x is 0, and they're saying when x is 3 and when x is 5. So I guess you could plug these in here, but that's a little bit harder to compute. Generally, you want to plug them into the original function. If I plug 0 in for all the x's, I get 1 over -4. If I plug 3 in, it would give me 4 over 9 minus 9 minus 4, which would end up being -1. And if I plugged in 5, that would give me 6 in the numerator and 25 minus 15 minus 4 in the denominator. That would be 10 minus 4 would be 6. what? So it doesn't look like we're, well, let's go ahead and do domain too. So domain is where three negative one. Oh, I This is okay, I didn't put it on the graph. Okay, so domain, this doesn't really help us with our graph, but there's two ways you have to take numbers out of the domain. Taking the square root of a negative number, you take out of the domain, but we have no square roots. And then also you have to take out numbers that give you division by 0, so that's undefined. So for the most part, you plug in any x value that you want to, but you can see that -1 and 4 both give me division by 0, so I have to take those out of the domain, which means I can plug in all of these values, all of these values, and all of those values. Really easy for me to write out the domain if I make that number and see the intersections. Everything from -infinity to -1, the numbers from -1 to 4, and the numbers from 4 to infinity. Alright, finish the graph. Looks like we're far from being done, but you can always plug in some more points if you want to. But really there's enough information here if you understand how it behaves around these asymptotes. So we know it hits these 2 points, so these are going to be connected. It doesn't hit the hole, but it will hit the points right before it and right after it. X can never be 4, which is why there's an asymptote here. So as it gets very close to 4, it's either going to go to infinity or to -infinity. So based on the direction of this graph, how this is slowly going down, tells me this one must shoot down to -infinity on this side, which means it's going to shoot up to -infinity on that side. When you get really close to dividing by 0, your fraction gets very, very big. Okay? And then this comes down and hits this point that we knew about. And then finally, the graph can cross a horizontal asymptote, but at the end of the graph, that's what it should be getting close to on the right side and on the left side. Now, the graph's probably the hardest thing to get to come together, because if you put the vertical asymptote in the wrong spot, or you get one of these points wrong, like I almost did, your graph often looks very confusing because the information is not matching up. But you can always plug in more and more points to get more and more values on your graph to build confidence if you feel like you need to. So now it's going to be, that's a lot of information, but now it's going to be some overlap. So this particular question wants to know where it's vertical asymptotes, where it's horizontal asymptotes. So horizontal asymptotes is where I said compare the degree of the numerator to the denominator. And since the degrees are equal, you should put y equals leading coefficient over leading coefficient. Very little work to be done, but you have to know what to do there. Vertical asymptotes are numbers that make just the denominator equal 0. So I would be interested in figuring out where's the denominator 0. I can do that quickly with factoring. I do have to make sure that those numbers don't also make the numerator 0, because then that would be a whole instead. But even without factoring in and figuring out what it is, I can see plugging in 3 is not going to make that equal 0, and plugging in -4 is not going to make that equal 0. Vertical asymptotes are vertical lines, so you need to write them as x equals. Horizontal asymptote is a horizontal line, and you do it as y equals. Okay, and then one more. We're going to go through all of that. So let's talk about, let's do the parts that I've already said once, so that will be a little more familiar. Sometimes we want to look at this. Sometimes we want to look at the factored form. The denominator is already factored for us, but the numerator could be written as x minus 4x plus 2. This is helpful because now I can see what numbers make the numerator 0 and what numbers make the denominator 0. Because if there's a number that makes the numerator and the denominator 0, that would be a whole. That didn't put this on this question, but here's the whole. No number makes the numerator and the denominator 0. Any number that makes just the denominator 0 ends up being a vertical asymptote. And that's an important piece of our graph. Graph it as a dashed line. And any number that makes just the numerator 0, this is really just a big fraction. And if you can make the numerator 0, 0 divided by anything is 0. And if you make this whole thing 0, then you're making y equals 0. And if you're making y equals 0, that's when you get x-intercepts. So the numbers that make only the numerator 0, not also the denominator because that would be a whole, end up being x-intercepts. So if you're required to make a table, you can go ahead and make 2 points for it. Okay, y-intercept is when I'm plugging in 0 for x, so this is usually the easiest thing. 0 minus 0 minus 8 over 0 plus 1 would be negative 8. Okay, and then we have something on the other page suggested that you set up a number line, write out the numbers that you can't plug in. I know I'm not plugging in negative 1 because that's conditioned by 0. It gives me a visual that I can plug in all of these and all of those. So the one thing that this page has that the other page doesn't have is for us to have enough information for our graph, we still need to talk about when does it have a slant asymptote and how do you go about finding the slant asymptote. So it will have a slant asymptote when the degree of the numerator is 1 bigger than the degree of the denominator. You always want to check that first because it's part of the work to find the slant asymptote, and most of them won't have one. The degree of the numerator is 1 bigger than the degree of the denominator. So this one does have a slant asymptote. And to find the slant asymptote, you have to use long division. So not a coincidence that we asked you to review that last time. X times x is x squared, x times 1 is x. Subtract all of this, so change the signs and add. Negative 3 times x is negative 3x. Subtract all of this, so change the signs and add. But there is one slight difference. So if I ask you to divide these, you should say that it divides to the quotient plus the remainder over the divisor. But the remainder has no bearing on where the slant asymptote is. So we actually don't care about this piece for slant asymptote. It will be y equals whatever the quotient is. Y equals x minus 3. So it's long division, except ignore remainder. But only if the degree of the numerator is 1 bigger than the degree of the denominator. Now that's really helpful for my graph because I can graph this as an asymptote, so I'm going to graph it as a dashed line. just like the last graph, feel free to put in as many points as you want to build in confidence. I actually already have enough information there because I can see that these 2 points need to be connected. The graph is going to behave the same way at a slant asymptote that it does at a horizontal asymptote, meaning that it can cross it if it wants to, but at the end of the graph, it should just be getting close to it. It's still going to behave the same way as the vertical asymptotes. It's going to shoot down to a negative infinity or positive infinity. And now that I can see the direction of this graph, I can see it shooting down to negative infinity on this side, which means it must be shooting up to positive infinity on that side, which is good because then that's consistent to hit this point that I want it to. And again, it's got to approach the slant asymptote at the ends of the graph. So I don't know exactly how fast this happens. I'm going to make a little bit of a guess, but I know this is going to hug up close next to that slant asymptote. Getting the graph to all fall in place is really the kind of last objective. You've got to be able to answer these questions correctly first before you can look at the graph together.